go, and then we'll just assume it's all right, and then I've got to stop and do another one in a little 20 minutes, so we'll see if it runs then. Okay, all right, well, thanks, and I will be bringing it back to solve it. Okay. Apart from when I discover that I can't actually move the... This is just absurd. All right. All right, where did we get? We got... we did keys, we did functional dependence. Right, I think we're here. Okay, sorry about that. I'm going to, as you've probably heard, I'm going to ask them to rebuild this machine. This is just too much hassle and wasting everybody's time. Okay, so we slowly slide further and further behind schedule. Relational database languages. Okay, so relational database management systems are software that implement relational database model. And we need to be able to interact with the model, the software model, the software implementation of the model. So we need some kind of language to communicate with the relational data model. And relational database languages can be divided into 3 types of languages. They're effectively wrapped up, and these 3 languages are implemented as one language called structured query language. But you require the language to be able to do 3 different types of things, and that's what these are. You need to be able to define data and your database. So you need a data definition or data description language. So that basically is create relations, define the fields on the relations, define the domains, the domain being the range of valid values within a field, create your own, define data types, create your own data types, impose constraints on the data in the relations, the foreign key, the primary key constraints. There are other types of constraints we'll meet in due course, not null, things like that. Create indexes, we'll talk about indexes to increase speed of access to data in the database. So you need a data definition language, sets your database up, allows you to set it up. You need a control language, which does things like define users, groups of users, and what they can do. So a language for controlling access to the information in your database. And finally, you need a data manipulation language, a language that allows you to add, delete, modify, and query data. SQL, as I just mentioned, structured query language, or I call it SQL, but I'm wrong, it's SQL. It's SQL, but my brain has the wrong, I call it SQL, but it's SQL is how it's correctly pronounced, which is the de facto standard language for relational manipulating and interacting with relational databases. It is an international standards organization standard, ISO standard, and I'll be explaining about standards and what they are in more detail throughout the course. And it, as I say, it implements both the definition, the control, and the manipulation functions in a single language. I'm going to skip over this to a certain degree because there's more. The rest of the lecture we're meant to be doing today is on SQL. So how does SQL query work? Well, basically, the most important thing that you'll be using, or the thing that you'll be using most, is called the select statement, which allows you to define how data is returned out of the database. So it returns data from one or more of the relations, the tables in the database. How does it work? Well, how does data get returned from the database? Well, it uses a combination of relational logic, mathematics, text and binary processing. So basically it calls a whole load of routines, libraries underneath the hood that do the hard lifting. And we'll talk about some of that in more detail in the next lecture. Importantly, an SQL select query will always return either a table or a relation, a new relation, or an error message, some kind of message. There's nothing else that it will ever return. It either returns a table or a message, or an error message. If there are no matches, so you do a query and nothing matches your query, then you get returned what's called an empty relation, a table with no columns and no rows, and a message. If you're doing a query that just returns one value, for example, you want to know the maximum cost of a car, that returns one value, maximum cost. It's returned as a relation with one row and one column. So even if it's a single value, it's still returned as a table. Important things about queries and SQL queries, are they live? So the data information is directly taken from the underlying database, not surprisingly. So as soon as if the data changes, the result of the query will change. Now for many databases, they're relatively static. Running the same query is going to return the same result. But if you're in a high transaction application, something like a supermarket checkout or something like that, any kind of shopping thing, anything where there's data changing all the time, every time you run the query, you're going to get a different result because the underlying data is changed. Doesn't matter, we can save queries unsurprisingly as things called views. So we use the select query in SQL to return data from the database. We go into a lot more detail. I'm going to talk a lot more detail about select statement in the SQL lecture that follows. As I say, one of the things is getting the data. So you write a query, you have to get the data out of the data tables. So the crudest thing you could do is simply scan every single row in every single table, and you would eventually get the result, the correct result. But scanning all the records in all tables can be very slow, and not surprisingly. You're doing things that you maybe don't need to do. There are quicker ways to access the information than simply scanning every row in every table till you get the result. And indexes, applying an index onto a table, onto a column in a table, is one way of speeding up queries. So they speed up queries by providing a shortcut to accessing the records. Indexes, it should be indexes rather than indices, are often tree-like data structures like this, which is called a B tree, and you basically build them to reflect the database state at a particular time. If the data changes, you need to then update the index to reflect those changes in the database, okay? So it's providing a shortcut record to the records in the database. So you have to run a program which basically builds the index. If you add more data, that new data is not embedded within the index automatically, so you'll need to rebuild the index. You can automate this so that every time a record is inserted, you update your index. Or maybe you update your index every day or something like that. So, when you update, how often you update your index is application dependent. This is a B tree index is an incredibly simple index. We're not really here to learn the details of indexes, but this is a quick example of how they operate. Okay, so it's a tree-like structure. Here are our records. This is ages, so these numbers are ages. So we've got one person who's 1, one person who's 3, one person who's 5, 6, etc., etc. So what the B tree does is it takes the middle value, the median value, makes that the root, and then it sort of indexes all the individual records. These are the individual records, I think these squares underneath. And basically, if you make a decision at each one of these nodes, you start at the root node and you move down the tree, following the decision as to whether it's higher or lower than a certain value. Okay, so we want to know people who are age 35 or above. If we were doing it sequentially, we'd have to go through every single record in our database and flag all the people who are 35 or over. And that would mean going through potentially 1 million records or something like that. However, if we've built a B tree and we start at the first node, we say, okay, is 13 is our value. So we say, is the person's age, or is the age group that we're after above or below 13? If it's below 13, we go this way, but it's above 13, 35 and above, so we go this way. We then have a decision whether it's between 13 and 17 or greater than 24. And we follow that. It's greater than 24, so we follow it to here. We then have a decision as to whether it's between 24 and 25, 25 and 30, 30 and 31, 31 and 35. You might be asking, why are these different? Why aren't these evenly spread? Well, it's optimized depending on the distribution of ages, rows in your database. So we can jump from here to here, and then we can access all the records. We have pointers from here that point to all the records, all the rows in the table where the age is greater than 35. So instead of processing potentially whatever this is, 1, 2, 3, 4, 5, 20 odd records, rows, we've gone 1 query, 2 query, 3 queries, we've got the answer. So in 3 steps, we've got the answer, whereas if we'd sequentially stepped through the entire table, it would have been 20 odd queries to undertake the same query. So potentially an increase in performance of an order of magnitude plus. So details don't matter, but the principle being is you can build a tree, you can link up and point to the various records with values above or below certain values, and that allows you to quickly search through the table. Well, you're not searching through the table, you're searching through the index that provides pointers that point you to the records, the actual records in the database. Just life. Okay, so that's indexes. So we can speed up with indexes. So these are the components that make up the database. What else have we got in the database apart from a query language, our structures, our indexes? Well, we can write things. Databases may be made up of things like user-defined functions and scripts as well. So this allows you, the use of functions and scripts allows you to automate database processing. And these come in a variety of flavors and styles. You can define functions within the database itself. So basically SQL queries that can be called repeatedly. You can write functions within the database that allow arguments to be passed, and we'll see examples of this. So this is more powerful. So if you want to get the maximum value age out of any table with an age field, you could pass in the name of the table, and then it would automatically find the age field and return it to you. And these things can be both written in sort of extensions to the SQL language, which we'll meet in more detail, but they can increasingly, you can call external libraries. For example, scripts written in Python programming language. Have you heard of the R statistics package? If you haven't, have a look at it. It's one of the most, it's probably the best open source statistics graphing package there is. And increasingly, Esri, in fact, about 2 weeks ago, announced a partnership with the open source R organization to strengthen the links between ArcGIS and the statistical strength of R. So effectively, they're writing programs or functions in ArcGIS where the actual analysis goes on in the R package. Basically, the Esri database, the data stored in the Esri geodatabase, it gets pumped out to the R program. The R program runs the does the analysis, and then it gets pumped back into ArcGIS. Important thing about functions and scripts is there's no standard, no international standard. Every database does it its own way. They've all got their own little languages. They're all idiosyncratic ways of doing things. So those are sort of functions embedded within the database. So these are all embedded within the database. They may call things externally to the database, but they're all run within the database. You can also write scripts in a programming language like, well, you could write it in Python, you could write it in Perl, you could even write it in R, that run outside of the database and then call into the database and do things inside the database. So maybe updating a whole load of records, you can do it programmatically from a script outside the database, or you can do it inside the database by doing writing functions. We've seen the command line. How do you interact with the database? Well, you need a means of interacting with the database. We've got our SQL language. Well, how do you actually type that SQL language into the database? Well, we've seen we can do it through the PSQL command line, or we could do it through some sort of client program like pgadmin3. Do you know what I mean by client? We're all clear what I mean by client versus a server. So Postgres is running as a sort of standalone little bubble. It runs itself on the machine. But to access and interact with that program, you come from another client machine or a client program that may be running on the same machine or a different machine that basically hooks into the database server and allows you to interact with it. pgadmin3 is not an integral part of Postgres. It's an add-on that you can use to interact with it. We've seen that, you've seen that. Okay, you're writing your script. What else have we got? How else do you interact with a database? Well, probably the most common way of interacting with the database for most users is through some kind of database form. They don't write SQL. 99.99% of database users probably don't even know what SQL is. They're interacting with databases through forms and interfaces specifically designed for interacting with that database, so some sort of graphical user interface. As I say, tend to be designed to meet specific user needs. So for example, within a company, you might have one graphical user interface for the customer services department, which allows people to view client information, edit it, enter customer and order data on a record by record basis. So somebody who wants to order a box of paper clips, you enter in a record for an order of paper clips. Whereas the supplies department itself maybe is interested in bulk orders from warehouses, how much supplies are in the warehouses, do we need to order more paper clips for the company? So they would have a different interface onto the same database. Finally, the management are not interested particularly whether there's enough paper clips in the warehouse today for the company, but maybe overall interested in how much money gets spent on paper clips each year and tracking whether we're buying more or less paper clips as the years go by. So these forms are designed for individual user needs. Here's an example, crude example. This is a form for onto a Microsoft Access database. It's crude. Well, I think they're quite crude, these, but you can see it involves, you've got a billing information this may be this graphical user interface may well be a view onto multiple tables in a relational database, of course. This may not be a simple mapping onto a single table. So we've got, for example, billing addresses, who we ship it to, whether it's Speedy or United or Federal. We've got historic, what products are being sent, quantities. You see the information. But it's laid out for the people who are to present the information that the people need to manage their sales and orders situation. This one is this is written in something called Visual Basic for applications within Microsoft Access. So it's a form that's written within the database program. So some relational database programs support the creation of forms. They have their own form building software library. So Microsoft Access does, also Oracle does, but Postgres doesn't. But increasingly as important is web-based forms, and that's what we are going to learn to do in the second year, or second term. So here we've got a map-based system with a couple of fields. We've got a field we can enter text in. We've got a button we can push, which will hopefully take us to the, in that case, the postcode. Then it maybe returns us the latitude and longitude for that postcode. Possibly we could also type numbers in here, press go, but I don't think it works like that. But the point being is you've got individual form elements that the user can interact with to return data from the database. So while forms are useful for entering and manipulating data and seeing individual records, they're maybe not very good for getting a summary of what the entire content of your database or some aspect of your database. So databases support what are called reports, or you can usually write, some databases support have reporting systems. And basically that allows you to summarize and present the data in the database as a document, in a document format. You can group records by different categories, provide summary statistics for them, and unsurprisingly, each time the report is run, it generates from the latest data. So here's an example of a simple form, or a simple report, which is a room, giving the history of room occupancy in some sort of hotel, so that you can get an overview of the room occupancy in the hotel. Forms, increasingly, in this day and age, support not just simply lists of text and summary tables. Increasingly, you can include all sorts of graphics and things like this automatically generated from your database. So here this is an IBM DB2 database with a DB manager, and it's built to provide longitudinal graphs of whatever these people are doing. What are they? Management agents and connection statistics. It doesn't really matter what it is. All right, quick summary of the relational model then. So the relational model, remember, is a theoretical design consisting of structures, relations, data types, index, operators that allow you to define and manipulate data, integrity rules that things like primary and foreign keys. Relational database management systems is software that implements the relational model, and that data within the RDM DBMS can be accessed through command line GUI-based interfaces. SQL is an international standard language for interacting with the relational model, but RDM BMSs vary in how much they implement the standard of the standard. And quite a lot of database functionality, some functionality is not defined by the SQL standards. So, for example, SQL standards do not define how a function should be defined in the relational model. So therefore, it's outside of the scope of the standards. Finally, on the relational sort of introduction to the relational model, Codd. Remember Codd? He was the guy who invented it in the beginning of the mid-70s, beginning of the 70s. The first implementations were a bit later. So basically, the relational model takes off. Lots of vendors start selling things, saying we're selling a relational database. Codd says, well, I don't think you're selling a relational database. You're selling something that has some things in relation that are similar to a relational model, but as far as I'm concerned, as the grandfather of the relational model, I don't think it's a relational database. So in 1985, he published 12 rules to define what a relational database is, according to him. Okay, it's actually 13 rules, 0 to 12, that define a true relational. What he says is a true relational Note some rules are controversial, e.g. rules through on theme-valued logic. So why is it 12? Is it 12 or is it 13 rules? Well, it's 12 and like one meta rule or one overarching rule, and that's rule 0. So rule 0 says for a system to qualify as a relational database management system, that system must use its relational facilities exclusively to manage the database. So that's kind of the definition, COD's hard definition of a relational database. Basically, it exclusively runs on the relational model. So the tables, so internally, it runs on the relational model as well. So users are stored in a table of users, permissions are stored in a table of permissions, etc., etc. No flat files, nothing like that to be called. And this is ensured if rules 1 to 10 are implemented of the other ones. And as I say here, very few software systems actually comply with all the rules. In fact, I suspect none of them do. I'm not going to go through these. You can look at these in your own time. Rules 1 to 12. So if you meet all these rules, you meet rule 0, and therefore COD says, hey, you are selling a genuine relational database. So do we care whether a database is actually relational or not? Well, that's a kind of an academic question. For most users, they don't. They care whether it does what they need to do, and don't care whether it meets this theoretical idea of what the relational level is. Well, just before we finish this section, so we're going back to, remember we looked at the other data models as well in very briefly, hierarchical network data models, some of the NoSQL models, the object model. So what are the limitations of the relational model? Because we have to make a choice between whether we want to take a relational model or use one of the others. So obviously one of the things is not all data is optimally tabular, that was mentioned before. So maybe you don't want, so one of the limitations of the relational model is when you've got non-tabular data, data that's better represented, more naturally represented as a network or something like that. It's very difficult to represent some types of relationship in the relationship model. As we'll see, spatial relationships doesn't work at all for them. And also it's rather bad at parent-child relationships, the things that the hierarchical model is particularly good at, parent-child relationships, and the network models as well. So it doesn't do very well on those. If you follow the sort of relational theory, adhere to it strongly, and do everything that what you could call the hardcore relational people say you should do, you can end up with a very complex data model and data structure, which is actually quite difficult to actually design in the first place and to build and to use. So if you do everything exactly like theory tells you, you quite often waste a lot of time producing an overly complex system, whereas you could have spent the time actually using the system to do something rather than building it and building this sort of large artifice. So basically don't get too hung up sometimes on following the relational theory in too much detail. Other problems, as we've seen, is scaling, particularly with moving into large data areas. Basically, the relational model can have problems scaling with large, complex data structures, and that was one of the big stimulations between the rise of the NoSQL movement. Oh, I am going fast because I'm trying to catch things up here. Okay, spatial databases. Okay, so we've seen the relational model. So what about spatial models? All right, that's what you're here for. It's only week 3, and we've mentioned spatial models. I don't think we see a map until week 7 or something like that. So what are spatial databases? Well, we know they store spatial information, geometric information. So there may be 2 or 3 dimensional geometric spatial information. First of all, while we can store spatial data in tables, it's not very efficient. Okay, imagine I could have shown you a diagram that showed how you decompose a polygon into its nodes, and then you store the left and right polygons to maintain topology. You'll probably see some of these diagrams in maybe the introduction to GIS lecture and things like that, or module. It is perfectly possible, certainly, to store vector data in a tabular system, the coordinates for the lines, points, and polygons in tables. It's perfectly possible to do it, but it's not very efficient, and you have to have complex queries to extract that polygon out from all those, from the node and the line tables and things like that. Indexes, standard indexes, relational indexes, like that B-tree index, they're indexes on one dimensions. Spatial data is two-dimensional or three-dimensional. So the standard index systems are not appropriate for spatial data. We'll see what we need to do for spatial indexing in due course. There aren't any, the queries that we want to make on spatial data are not supported in the standard relational model. So we want to return geometry. We don't want to return, geometry isn't particularly a table, is it? It's some kind of, you've got to, it's not immediately apparent how you return a geometry simply as a table in a tabular format with fields and columns. It's possible to do, but we need functions that actually do these and return geometries based on spatial overlay, distances in 2 dimensions, things like that. So we just simply don't support the query functionality in the relational model. So when GIS began, late 60s, second half, end of the 60s, roughly in the same time that the relational model was starting to arrive, this diagram sort of shows the basic, what we call architecture of a GIS. So we used to have, so basically the relational model wasn't any good for storing the geometric data. So what the companies like Esri did was they created their own special spatial database specifically designed for storing the spatial information. So it had geometry, it had spatial indexes, and also it stored attributes associated with the geometry. So that was in a special database, and then they built software that sat on top of that database and talked to the database. So this is we had software that sat on top of it. Now, what is the separation here? Well, this is the database. So this stores the geometry, the indexes, and the attributes. So this is merely storage. The database engine in this diagram is basically the query engine. So this is how you query it, how the spatial queries are undertaken. And the GIS tools is the interface that sits on top of that. Yep. So at the bottom, we've got the data. In the middle, we've got the thing that does the processing on the data. And then on the far end, we've got the tools you interact with that calls the engine that then accesses the data, does the data processing, and returns it. And in the first generation GIS, these were mostly commercial products, all commercial products. And these all were very closely linked through, this is called, you know what I mean by proprietary? Proprietary is something that's owned by somebody. So a proprietary API is a private, written by a company, say Esri or someone like that. So, for example, this might be an Esri file geodatabase. This might be part of the ArcGIS system. This may be ArcMap on top that you're actually using to view the data. So in the first generation, basically, it was all this standalone system that came in a box. You took it, you installed it, and it was called a GIS package. Everything was together. Everything was closely linked. And they were also quite self-contained. It was difficult to break out of this silo to connect with other pieces of software. So that's how it started off. But of course, many companies, so first of all, it was, wow, it's amazing. We can actually see our geographic data on the screen and interact with it. Isn't that brilliant? Because you couldn't do that before. before, if we wanted to do spatial overlay, we'd be standing there with bits of tissue paper and pens and papers and spending hours and hours hand connecting the data through it spatially by hand. Now you could actually do it on the computer. But of course, so companies sort of set up their GIS databases to deal with their spatial information, but often they had other data that wasn't inherently, or they didn't need to be spatialized all the time in other corporate databases, in relational database systems, corporate relational database systems. So for example, I started work, I've told you this already, in the water department in Edinburgh. So we used to have a GIS for the water mains and the thing where the pipes were, but there was also, but that was separate from the data to do with the costing of putting in new infrastructure, putting in new pipes, putting in new valves. There was a whole separate corporate system in an external standard relational database. So in the mid-80s, basically, they started implementing, connecting your traditional relational databases through SQL links, standard structured query links, through to integrate it with your spatial data. So you still had this sort of standalone GIS system, but now at least you could grab some data out of a corporate relational database which was non-spatial and link it in. So SQL started to come in here. Everything else was being done with proprietary algorithms, sort of custom algorithms and software for doing the exchanging the information, spatial information. So that's great. We're starting to integrate and bring data together in different database systems. So we're now sort of approaching what we can call the third generation down the bottom here. So this is all very well and good, but we've still got a separation between our spatial data and our aspatial data. We're using different languages. We're using SQL here. We're using some proprietary language to talk to the spatial data. We're using a different language to talk to our aspatial database. Can't we just have one language that talks spatial and no spatial together? And that was the idea. Why do I have to maintain two databases? Can't I maintain one database? Isn't that much more efficient when it comes to my organization? Not surprisingly, it is. So what happened was the relational database management people saw an opportunity, or there's an opportunity there. How do we integrate these better together? Well, so can we implement a spatial functionality in a relational database? And that's what started to happen. So basically, we started to extend SQL to include functions and data structures for storing spatial data actually in a normal relational database system. And that's kind of the situation which we're now in with Postgres, for example. So we now have one database, which is a relational database management system, something like Postgres, that both stores the spatial data in a spatial data model within the relational database and normal relational data tables as well within a single database. And we use the spatial analysis functionality, which used to occur outside of the database in software that accessed the data in the spatial database, has been migrated actually within the spatial database itself. So whereas before you would grab your data out of your database or add your aspatial database, then do your analysis outside of it because it involved spatial queries which weren't supported in your relational database here, this functionality has now been migrated within the relational database, and your tools just use one language, SQL, to communicate with your database, with your underlying data, and to do the query. So we've had this slow increase or change in the architecture and the connection between the two systems. Oops. Okay. What this generally allows us to do, and I've talked about this earlier in the beginning, is this ability to separate the tools, the graphics, the user interfaces from the data and the databases and the processing underneath, is the separation of function. So the database, all the data is stored in a relational database, which deals with the structures, the storage, the indexing, the security, and the query onto the data. The applications, which can differ, plug into that database, and they do things like support data loading, editing, visualization, mapping, and analysis. These are much more user-dependent functions than these. These are sort of generic underlying functions. So we can bolt all these different GIS applications onto a single database, resulting in different architectures, which is what this attempts to show. Okay, so taking this apart, so today you can buy ArcGIS. ArcGIS comes with a database, a relational database, the file geodatabase model. It supports the analysis side of things, all the Arc toolbox functions and things like that. It also supports the mapping functions, ArcMap, ArcScene. And you buy that as, it might be sort of slightly different programs, but basically it's sold as an integrated package. That's like version, remember the first generation GIS. Increasingly though, we move more towards a component-based architecture. So for example, I could store my data in MySQL, a relational database that has some support for spatial functionality. And maybe I plug into it with the open source QGIS package, and I do my mapping and my analysis in QGIS, but the data is stored in MySQL. So I don't do any analysis query in the database. All the query goes on outside in QGIS, or at least the interaction that generates the queries. Alternatively, maybe I use the Leaflet JavaScript mapping API, which we'll be using in the second term, as my mapping interface in a web browser. But all the data is stored in Postgres, PostGIS, which is the Postgres spatial extension to Postgres, and perhaps all the functional analysis also goes on in Postgres. So I don't do any analysis in my mapping application, but all the analysis goes on in the database. Or I could store my data in a MySQL database or a Postgres database. I could build my mapping interface. I could have my map using a program like Mapnik or something like that. Mapnik's a kind of semi-desktop, semi-browser-based. Can't say I'm an expert in its use, I've just come across it. But you can use it for mapping. It's particularly designed for internet-based mapping, if I remember correctly. So maybe you do your mapping in there, but maybe you'll do analysis in a JavaScript library like Shapely, but your data's in the database. Now, which one of these you choose depends on what you're trying to do for whom, where, and when. They're not necessarily better than each other. It's just that it's possible to distribute the data, the analysis, and the graphical functions in different ways across different bits of software. Just to summarize quickly. Okay, database model summary. So we know alternative database models address different data problems. For example, volume versus complexity, structured data versus unstructured data. Unstructured, if you remember, is things like papers and text, free text. One should select the most appropriate model, database model, for the task in hand. But this is conditional on limited resources, time, knowledge, corporate policies, etc., etc. So while ideally you might say, well, I'd love to implement that as a graph database in Neo4j, the reality is you may be constrained by organizational or other constraints, which means you, in fact, have to implement it as with the relational model. DBMSs separate data from application, allowing component-based solutions, as we've just seen. Spatial data requires a special spatial model. as I say, these have now been implemented in some relational database management systems to a greater or lesser degree, Postgres being one of the most advanced, if not the most advanced, open source spatial data model. But also some of the NoSQL models are now starting to have space included in them as well. So space is becoming something that's becoming widely implemented across all models. All right. Okay, let's hope that's recording. Okay, let's take, can we just take 5 and then we'll get on with the, do you want to take 5? 5 minutes? Yeah. And then I'll get on with SQL and move on with that. Let's see.